Hey everyone, welcome. So today, we're going to dive into something that's actually way more intuitive than it sounds, the decision tree. It's a powerful tool in data science, but what's so cool about it is that it basically mimics the way our own brains work. And by the end of this, you'll see just how simple, yet powerful, this idea really is.
Okay, so let me ask you something. Think about the last really big decision you had to make. Something like buying a car, picking a new job, maybe even deciding where to live. How did you actually go about it? You probably didn't just stare at the wall, right? You broke it down. Let's say it's a job offer. You'd probably ask yourself, okay, do I have any other offers on the table? If the answer is yes, your next question is probably, well, is that other offer better? Each answer you come up with leads you down a different path, until finally you land on your final choice, accept or reject. And boom, just like that, without even realizing it, you've basically built a decision tree right there in your head. That logical, step-by-step process, that's the exact same idea behind this super powerful data model. All right, so now let's take that idea, that human intuition, and see how we can turn it into a structured model that a computer can actually understand and use to make some pretty amazing predictions. So what is a decision tree officially? Well, at its core, it's basically just a flowchart. You can think of it as a model that asks a series of branching questions, kind of like a game of 20 questions, to narrow things down and finally land on a conclusion or a prediction. And every tree has the same basic parts, its anatomy, if you will. It all kicks off with the very first question, that's called the root node. Then each answer you give, like yes or no, takes you down a branch. That branch can lead to another question, which we call a decision node, or it can lead to the final answer, the end of the line. That's called a leaf node. Okay, this is where it gets really cool. It turns out you can use these trees for two totally different kinds of jobs. You can either use them to sort things into buckets, or you can use them to predict an actual number. Let's dig into the difference.
On one hand, you've got classification trees. They're all about answering the question, what kind of thing is this? Think, is this email spam or not spam? Is this transaction fraud or not fraud? It's all about putting something in a category. On the other hand, you have regression trees. They answer the question, how much or how many? Like, what's the price of this house going to be? You're predicting a number, not a label.
All right, let's make this real. Let's look at classification in action. Picture this. A company wants to figure out, in a split second, whether to show you an ad on your phone. A decision tree is perfect for this. So the tree just follows this super logical path. First question, is the user in a supermarket? Yes. Okay, next question. Are they 40 years old or younger? Yep. Last question, do they have a college degree? Yes again, and based on that specific path, the tree reaches its final decision, its leaf node. Send the ad. Simple as that. Okay, so that was classification. Now let's switch gears and look at the other flavor, regression. Remember, here we're not trying to pick a category, we're trying to predict a real continuous number. And the classic example for this is predicting a house price. So the tree starts asking questions to narrow things down. Does the house have 2 or more bedrooms? Yes. Does it have only 1 bathroom? Yes. Does it have just 1 parking space? Yes. Now, see what's happening? This specific path isn't leading to a yes or no answer. It's isolating a very specific group of similar houses from all the data it's seen before. And here's the key difference. For that very specific group of houses, the tree doesn't spit out a label. It looks at all the houses that ended up in that leaf node and calculates their average price. In this case, it predicts a value of $180 per square foot. That right there is a regression tree doing its thing. So this all looks pretty neat and logical, right? But it kind of brings up a huge question. I mean, how in the world does the tree know which questions to ask in the first place? And how does it know the best order to ask them in? Yeah, think about that for a second. Out of all the possible things it could ask about, age, location, square footage, number of bedrooms, how does it learn to pick the one question that's most powerful to start with? What's the secret sauce? Well, the magic behind it is an algorithm, and the most common one is called CART. Now, here's what it does. At every single step, it looks at every possible question it could ask. And then it picks the one single question that does the best job of splitting the data into the most pure groups. The one that creates the cleanest separation between, say, the yes answers and the no answers.
The whole goal, its entire mission, is to reduce what we call impurity or messiness. It starts with a jumbled up group of data at the top, and then it obsessively searches for the one single split that will create the cleanest, most organized subgroups possible below. It's trying to get as many of the yellow circles in one box and as many of the blue squares in the other. That's literally how it learns, by getting better and better at sorting.
Okay, so a single decision tree is fantastic, but it does have one big potential weakness. So, of course, data scientists came up with a really brilliant solution. The thinking was, if one tree is good, what if we used a whole forest of them?
Here's the problem. It's something called overfitting. A single tree, if you let it grow too deep and complex, can basically memorize the data you show it. It gets a perfect score on the test, but then when you show it some new data from the real world, it completely bombs. It's kind of like an expert who's so hyper-specialized that they just can't handle any new or slightly different situation.
And the solution is just beautiful in its simplicity. Instead of relying on one single overly complicated expert, we build what's called a random forest. We create an entire committee of many, many different, simpler decision trees and let them work together.
So here's how it works, and it's pretty clever. First, you create hundreds of these simple little trees. But here's the trick. You don't let any single tree see all the data. Each one only gets to train on a random little piece of it. And there's another layer of randomness. At each decision point, each tree is only allowed to consider a random handful of features to split on. This whole process forces the trees to be different from each other, which makes the forest super strong and reliable. And for the final answer, they just vote. The majority wins. All right, so let's bring this all home. After all this, why should you care? Why are decision trees and random forest so incredibly popular and important? Well, it really boils down to one absolute killer feature. Their number one superpower, especially compared to a lot of other complex models, is that they are so easy to interpret. They're not a black box. You can literally follow the path down the tree and see exactly why it made the decision it did. Plus, they're super flexible, they don't need a ton of data prep, and once they're trained, they make decisions in a flash. And that really brings us full circle, back to where we started. See, decision trees aren't some scary, complicated thing. They're really just a reflection of clear, step-by-step logical thinking. So the next time you're facing a really big decision, maybe just ask yourself, what if this was just a simple tree? What's the very first, most important question I need to answer to start splitting this problem up?